Free space optical communications relies on a powerful and precise light source, the laser. Understanding the inner workings of a laser is key to grasping its critical role in FSO system. Let's start with the diagram on the left, which illustrates the essential components of a laser. So, at its heart, laser is an optical oscillator. An optical oscillator is an optical amplifier with a positive feedback loop. So the idea is that oscillation process is initiated by the presence of a small amount of noise, in this case, small amount of photons. Input is amplified and is fed back into its amplifier. Increase in the signal is limited by the saturation of the amplifier gain. Well, you may say that this is a very abstract representation and this is not how laser works. And it indeed works a bit differently. But at its heart, that's the main block diagram that we need to understand. Well, at its heart, laser is composed of an active medium, which can be thought as amplifier. So what it does, it amplifies the signal. That's the core element, often is a crystal, gas, or semiconductor, is where light amplification happens. Well, it has to also have this feedback mechanism, as we see here. So the feedback mechanism on both ends are partial transmitting mirrors. Mirrors at either end of the active medium create a resonant cavity, bouncing light back and forth to simulate further emission. We also need to have some sort of pump source. This provides the energy needed to excite the atoms or molecules in the active medium, creating population inversion necessary for lasing. This setup creates a feedback loop where a small amount of noise or spontaneous emission in active medium is amplified as it passes through. A portion of this amplified light is reflected back by the mirrors, intensifying the light with each pass. This amplification continues until a steady state is reached, producing a coherent beam of light with a specific wavelength and phase. It is a highly directional and monochromatic beam that makes laser ideal for FSO, enabling long-distance communications with minimal divergence. Free space optical communication systems rely on efficient and reliable light sources, and laser diodes have emerged as the workhorse of this technology. Let's delve into the characteristics that make laser diodes ideal for FSO applications. Here the diagram on the left illustrates the basic structure of a laser diode. It consists of a semiconductor p-n junction, where electrons and holes recombine to emit photons. The cleaved surfaces on the semiconductor act as mirrors, as saw previously, forming a resonant cavity that enables simulated emission and amplification of light. So the graph on the right depicts the input-output characteristics of the laser diode. A crucial parameter is the threshold current, a threshold, below which only spontaneous emission occurs. When the current exceeds E threshold, simulated emission takes over, resulting in a sharp increase in optical output power. This characteristics allows for efficient modulation of the laser diode output, make it suitable for high-speed data transmission. Well, type and characteristics of different laser diodes. This table summarizes the type of laser diodes commonly used in FSO, classified by their material composition and corresponding wavelength. So first of all is gallium arsenide laser operating in the 780-990 nanometer range. These are suitable for short-range terrestrial links due to availability of inexpensive silicon-based components. Indium gallium arsenide with wavelengths between 890 and 980 nanometers. These diodes offer higher power output, often used in master oscillator power amplifier configurations for increased range and reliability. And third one, indium gallium arsenide phosphor operating at 1300 nanometers and 1550 nanometers. These are preferred for long-range links and space-based applications due to their superior atmospheric transmission characteristics.